Hello, my name is Joe Houpt. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. This presentation is on generalized assessment functions based on Grice Representations, and this is work in collaboration with Cara and Kneeland at Wright State University. There are many instances in which we are interested in how people combine multiple sources of information to make a decision or act. In many of those cases, the efficiency with which people combine the information is informative about the underlying cognitive processes. This can range from very simple stimuli, like flashes of light on an otherwise dark screen, to more complicated stimuli such as parts of a face, cross-modal stimuli such as light and sound, or other applications like the fusion of different sensor information for practical applications. One approach to assessing information usage across multiple sources is the collection of assessment functions proposed by Townsend and Altieri in 2012. The assessment functions are based on the logic of capacity coefficients, where a baseline model predicts how a person would perform, assuming they use unlimited capacity, independent and parallel processing. And it jointly predicts that performance for choice and response time, and hence balances to some degree accuracy and speed. As is demonstrated here, these formulas end up becoming a little bit complicated. Furthermore, there are a number of the formulas, and I'll return to that issue in a moment. Amongst the formula, there are different types of assessment functions, those focused on correct responses and incorrect responses, and those developed based on the survivor functions, which are labeled as fast in the paper, which are labeled as slow in the paper, and those labeled as fast in the paper, which are dependent on cumulative distribution functions. And the rough idea here is that there's a prediction of performance of the USIP, unlimited capacity independent parallel model, and then performance is plotted relative to that model, where a higher level indicates more efficient, a lower level less efficient, and that's a positive thing for correct response times, and perhaps undetermined for whether the incorrect response assessment functions are higher or lower than the baseline prediction. There are some clear limitations of assessment functions. One is that there are no established inferential statistics for the analyses. Hence, analysis tends to be qualitative or rely on secondary assessments of the functions, such as functional principal components analysis. Another issue is that there are many different functions for similar analyses. For example, the full combination of correct and incorrect and fast and slow. And finally, these equations are rather complicated. Although they're not awful to estimate from data, they're certainly complicated to communicate. To propose an alternative view on assessment functions, we're going to build models based on the Grice representation. The Grice representation of a choice and response time assumes a deterministic accumulation process or processes with a random threshold. For example, in the left plot, the red solid line would be a deterministic accumulation process, and the red dashed line would be an example of a random sample of a threshold that determines the response time. In this case, it's the point at which the threshold crosses the accumulation process at approximately 100 milliseconds. The right graph illustrates what this might look like for a two-choice situation, where the blue lines are associated with one choice and the red lines associated with another choice, and the solid indicates the accumulators and dashed a random sample of the threshold. Whichever accumulator finishes first, in this case the threshold for the blue process crosses the standard or the deterministic accumulator slightly before the threshold for the red process crosses its accumulator. Hence, the blue choice would be the one executed representing, an execution of the blue choice is what's represented in this graph. And the response time would be slightly faster than 100 milliseconds. Perhaps that crosses at about 90 milliseconds. Javarov showed in '93 that this Grice representation can be a universal model of choice response time distributions. Furthermore, it allows for the comparison of constraints across models and common framework, as argued in Jones and Javarov 2014. Formally stated, the response time t can be viewed as the inverse exponential distribution function evaluated at this 1 minus e to the negative h I of t, where h here is the hazard function. So Javarov in '93 showed this is the case where effectively you can choose any distribution you want for that threshold process, but if you choose the exponential 1 distribution, then that deterministic accumulator process is actually the cumulative hazard function. So that's effectively what's being communicated by this formula. So taking that approach, we can look at how we might model a USIP situation. Generally speaking, we're going to work with each channel has its own deterministic accumulator and a random exponential 1 threshold following that Grice representation outlined in the Javarov '93 paper. And then we combine channels according to the assumptions of the unlimited capacity, independence, and parallel processing model. And then the specifics of the combinations of those processes across channels depends on the task. For example, whether it's a discrimination or detection task, or an AND task, much in the same way the existing assessment functions depend on each of those aspects as well. To estimate this USIP model from data, again, we have each accumulation process as a cumulative hazard function. And an observed response time is an observation of the process associated with that observed response, or a censoring event for the other process. This allows us to estimate the channel correct and incorrect accumulators with the Nelson-Olin estimators of the cumulative hazard function applied to the response when only that particular channel is active. And here I have formulaically indicated the Nelson-Olin estimator. It's something I've written about in other papers and would be happy to discuss in the questions session in the live conference, or feel free to email me about these as well. Once we have a statistical estimator, one last point here is that because we have this statistical estimator and we have both the mean and the variance, we can then derive statistics based on this. And for those of you that are familiar with this, the statistics end up being very similar to the statistics used for the capacity coefficients and the capacity z-scores. One critical assumption that we'll need to make for this analysis is how to compare an observed performance with the multiple source of information against the predicted USIP performance. To address this question, we do so in terms of what we call the Grice space. So in this space, we have a parametric curve here that's parameterized by time in a two-dimensional space where one dimension represents the correct cumulative hazard function and the other represents the incorrect cumulative hazard function. One option for measuring efficiency in this space is to create a plane representing equal efficiency based on multiples of the estimated USIP. So here I represent that as a parametric curve where we've got both time for the G function or Grice function for the USIP model, and then x, where x would be any positive number. So effectively that carves out a plane in that two-dimensional space. And then we can use whatever the x is that minimizes the distance between the USIP prediction model at x and that Grice parametric curve for the observed performance. An alternative approach would be to create a similar surface, not necessarily a plane, but a surface in that Grice space using parametric variation in an accumulated model. For example, looking at the full range of potential drift rates in an LBA model or drift diffusion model. The derivation of the USIP models can vary in complexity when we look at it analytically. A discrimination task, it's fairly straightforward. The cumulative hazard functions just sum. So the correct cumulative hazard functions for each individual channel, sums for the correct cumulative hazard for the USIP channel, and the incorrect cumulative hazard function sum for the incorrect cumulative hazard function for the USIP. Things are a little more complex for the detection task, or at least at first blush. So we can use the logic of a USIP model and parallel OR processing and detection to get an idea of what the density for a correct USIP response time would be. So that's demonstrated here. Importantly, on the right-hand side of the equality, the F's indicate the exponential 1 density, S, the survivor for that distribution, and F, the cumulative distribution for that function. So we get a little bit of simplification, even if it doesn't look like it, for sort of plugging in that distribution function. And then we can do some algebra to combine terms and end up with a relatively simplified representation of what the density of a USIP correct response time would be in this space for a detection task. And notice this has sort of an inclusion-exclusion form. And then this could be used to derive the cumulative hazard function, which in turn could be, in a similar process for the incorrect could be derived as well, which gives us that parametric curve in the Grice space, which we could then use for carving out that plane for comparison against performance observed with two sources of information available. Okay, so with this project, what do we have so far? We've proposed a general framework for representing USIP predictions. This framework affords the use of well-known statistical estimators that are also implemented already in the handy SFT-R package. This framework also has the advantage of relying on exponential distributions, which allows us to simplify at least some of the analytic derivations of the USIP models. We've also proposed a framework for scoring performance against a USIP baseline. The parametric version that involves having sort of best fit parametric models and then a space carved out by varying the goodness parameter in those, or specifically the drift parameters for LBA and DDM, as well as a sort of semi-parametric score that depends on just sweeping out the plane by multiplying the observed Grice curve, or curve in the Grice space. Critical next steps are going to be to complete the derivation of USIP predictions for all of the stopping rules and detection discrimination combinations, and to implement the analyses and statistical tests in the SFT-R package. Thank you very much for your attention to this presentation. I look forward to feedback and continued efforts on this project with my collaborator, Cara. I'd also like to acknowledge the funding support we've had for this work, including NSF and the Air Force Office of Scientific Research.